The most commonly used metric for evaluating classifiers is its accuracy. However, there are certain conditions in which accuracy is not the best measure. When would you use something other than accuracy to determine how well a machine learning model performs? In this lecture, we'll talk about subtleties involved in classification and how other metrics beyond accuracy, metrics such as precision and recall, might be good measures based on what your problem statement is. Precision and recall are alternative measures which allow you to figure out how well your machine learning model performs. Let's say you have what I'd call an all is well binary classifier. Whatever information you feed in, and in this particular case, it happens to be medical reports, this machine learning model will always say, no problem, everything looks fine, I can't detect any cancer. This is a machine learning model which always classifies your medical reports as normal. Now, the problem with this classifier is that, especially if the cancer is of a very rare form that it's supposed to detect, the accuracy for this model might be 99.9999%. This is because a vast majority of the people in this world do not have this rare form of cancer. The accuracy is high, but really, would you trust this machine learning model with your medical reports? Not really. In this particular situation, based on your problem instance, this all is well machine learning model cannot be evaluated correctly based on its accuracy. And the more general reason for that is the labels that are fed in or are possible outcomes for this learning model are skewed in that there are some labels which are much more common and some labels which are very rare. It's very common to have a label which says no cancer and rare for the label which says cancer. Such a data set is said to be a skewed data set. This data set is skewed in favor of labels which says there is no cancer, which is why, even though the accuracy is high, it's not a good measure to evaluate this model. Accuracy is a poor evaluation metric here, and this is true for any skewed data set. Let's say you were living in Bangalore, which has a terrible traffic problem. The road is always filled with cars, and you were to give a yes no answer to, is there a lot of traffic today? If you answered yes, the chances are 95% of the time you'd be right. But really, that doesn't give me much information. But we still need to measure whether a model is a good one or not. This is where other metrics come in. And in order to understand these other metrics, what you'd have to set up is something called a confusion matrix. The confusion matrix has two axes. Along the top axis, we have the predicted labels. The predicted labels are the outcomes from our machine learning model, the predictions that our model has made. The possible predictions here are cancer and no cancer. On the y axis, we'll put down the actual labels. The person whose medical reports we fed into our machine learning model, did the person actually have cancer or not? Once our model has been fully trained, let's say that we've passed in about 1,000 medical reports into our machine learning classifier, and we get a 4 by 4 grid based on what the predicted labels were and what the actual labels were for our inputs. Let's say we go ahead and fill in this 2 by 2 grid. There were 10 instances where cancer was actually present and it was also detected by our machine learning model. There were 5 instances where there was no cancer, but our model still predicted cancer. There were 4 instances where cancer existed but was not detected, or our machine learning model missed it. And there were 1,000 instances with no cancer, and our model basically said no cancer. Look at how this data set is heavily skewed towards no cancer. 1,000 instances where there was no cancer and no cancer was predicted. This seems to be a highly accurate machine learning model. Let's use some technical terms to describe each of these cells within our grid. Where our machine learning model predicts cancer where cancer exists is called true positive. Cancer existed and the medical report was enough for our machine learning model to diagnose cancer. Actual label is equal to predicted label. Then there are 5 instances here where no cancer existed, but our machine learning model somehow believed that the person did have cancer. Actual label is not equal to predicted label. This is a false positive. The machine learning model was positive, but it was false. So, false positive. And there is, of course, the driver of the high accuracy of our model. 1,000 instances where no cancer was present in the individual, and our machine learning model correctly flagged it as no cancer. These are the true negatives. Negative because our machine learning model did not predict cancer, and true because it matched the actual label. Actual label is equal to predicted label here. And finally, we have the four instances here where cancer was actually present, but our machine learning model completely missed it. Our machine learning model's prediction was no cancer. Actual label is not equal to predicted label here. This is false, and it's a negative. It's a false negative because our machine learning model did not predict cancer. And this forms our confusion matrix, which we'll use to evaluate how well our classifier performs. Now, in order to understand and remember how these terms apply, remember that whenever the predicted label is cancer or a positive label, it is a positive, and whether the label matched the predicted label indicates whether it's true or false. The first column here are both positive because our predicted label was cancer. The second column are both negative because our predicted label was no cancer. Now, our standard measure for how well our classifier performs is typically accuracy. Now, when we are considering accuracy, we only consider those cells where the actual label was equal to the predicted label. So, we consider cells along the diagonal that you see highlighted, where we have true positives and true negatives. True in both cases because actual label was equal to predicted label. Accuracy is basically the fraction of the instances that fall within these two cells. So you can basically express it as a very simple formula. True positives plus true negatives upon the total number of instances that were fed into your machine learning model. In our case, it's 1010 upon 1019, which gives us an accuracy of 99.12%. This is a highly accurate machine learning model, as I said earlier. Now, even if I hadn't mentioned it a gazillion times before, instinctively you know that this isn't a great machine learning model. Even though our accuracy is 99.12% and the classifier gets it right so very often, there is an implicit but here. Take a look at this confusion matrix and you'll notice that in all our examples, there are five people who have probably been put on chemotherapy or radiation or some other treatment for cancer when it was totally not required. False positives in this situation extract a huge toll and are immensely disruptive to the people whose lives are concerned. On the other hand, there are four instances where cancer actually exists, but it has gone undetected. Cancer has not been detected, no treatment has been prescribed. This once again takes a huge toll. Our machine learning model got it wrong for a very crucial set of people. So, accuracy here is not a good metric to evaluate whether this model performs well. You can't be satisfied with this model. You need to use other metrics to see how well it performs and see if it's indeed a good model. Now that we've rejected accuracy as an evaluation metric for this machine learning model, we need to replace it with something better, something that will actually represent whether this model is good or bad. And one of those metrics can be precision. Precision basically considers all the instances in the first column that you see highlighted. Precision is the accuracy of the classifier when the classifier claims that cancer exists. Accuracy when the classifier flags cancer is precision. This is the definition of precision. Precision can be thought of as a measure of exactness or the quality of our prediction. When our model claims there is cancer, how accurate is it? In order to measure precision, you only need to consider the two columns that are highlighted. That is when our model has flagged cancer. Precision is the true positive rate divided by the total number of positives. Here, this is 10 divided by 15, and it is 66.67%. The numbers don't look so good anymore, do they? When you say that the precision of our machine learning model is 66.67%, what it essentially means that is that 1 in 3 of the cancer diagnosis that our model makes is incorrect. You can clearly see here that this is not really a machine learning model you'll trust, because it gets things wrong one third of the time. One in three people on chemotherapy or radiation because of this model are in it for no reason. They don't require it. Other terms that might be used to define precision are positive predictive value or positive prediction rate. Another metric that could be used to evaluate classifiers is recall. Recall basically looks at all of those patients who actually had cancer and then checks to see what fraction of those patients were correctly classified by our machine learning model. So, recall is the accuracy when cancer is actually present. Recall is also said to be a measure of completeness or quantity of the number of people who had cancer. How well was our machine learning model able to detect cancer in those patients? What is the fraction of patients that were left undetected? So, recall can also be expressed using a formula. Consider only the cells that have been highlighted, the true positive rate upon the true positive plus false negative. In our case, it's 10 divided by 14, which is 71.42%. Once again, recall doesn't make it seem like this is a very good machine learning model. A recall percentage of around 70% basically means that out of every 7 cases of cancer that were fed into our ML model, the model completely missed two, wasn't able to detect cancer in two of them. If the data set that you feed into the training process of your machine learning algorithm is a skewed data set, that means if there are two labels that your model has to classify data into, if one label is extremely common and the other label is extremely rare, that is an example of a skewed data set. Accuracy is not a good metric when you're evaluating machine learning models built using a skewed data set, or when the problem statement in the real world will have a skewed data set. This is because you can get a very high accuracy by predicting the same thing, the most common label, over and over again. But this will not discover the rare cases where the outcome or the actual label is the less common label. And if your real world scenario is something like cancer detection, where you're detecting a very rare form of cancer, then the consequences of using a highly accurate model, which does not do well on other metrics, can be pretty bad.